Welcome to Hovercraft Physics and Chemistry for a video on momentum. Specifically, we will look at why momentum is conserved and why you should care. First, we should talk about what it means to say that momentum is conserved and the evidence that momentum is conserved. In my previous video, I showed you how to do a video analysis to calculate the momentum of carts before and after a collision. This graph shows the total momentum before the collision compared to the total momentum after the collision. And we see that the slope of the relationship is nearly equal to 1. What that means is the total before and the total after are equal. For example, this cluster of data points falls around 60 units of momentum before collision. And because the slope is 1, total momentum after the collision is also essentially 60. So this is something that we can do in isolated collisions between objects, and we'll find time and time again that the total momentum of the objects before the collision is equal to the total momentum after the collision. That's what we mean when we say momentum is conserved. So why does this happen? We need to consider Newton's second law of motion. Most people know it as F equals m times a. If I had the ability to write all the physics textbooks, I would teach it like this, that acceleration equals F net, the amount of unbalanced force on an object, divided by its mass. That means if you increase the unbalanced force on an object, you'll increase its acceleration. But if you increase its mass, it has more inertia. That will decrease the acceleration. Let's go back to the more familiar form, and I'm even going to drop the net part on the force. So this equation just looks at an individual force and relates it to the mass of the object that the force is being applied on and the acceleration that it will produce. To tie this into momentum, we need to take the definition of acceleration. Acceleration tells you how much velocity changes per unit time. In other words, we can replace the acceleration term with delta v over delta t. Delta just means change. So acceleration is the change in velocity divided by the change in time. You can already see that part of this equation is looking like momentum. Momentum is the mass of an object times its velocity. We see that here. Mass is in this version of the equation, and velocity is as well. We'll need to do some rearranging to get this into the final version that I'd like to look at. Let's multiply both sides of the equation times delta t. That's going to cause the delta t on the right-hand side to cancel, and we also realize that force would be multiplied by delta t as well. Let's clean that up a little bit. That's better. I'll move it to the center and put a box around it. This is the equation that we need to think about. It's just a restatement of Newton's second law of motion in terms of momentum. The left-hand side of the equation, F delta t, is actually called impulse. It's the amount of force applied on an object multiplied by the time interval that that force is applied. That should equal the mass of the object times its change in velocity. Notice that the right-hand side of the equation is now mass times change in velocity. Since momentum is mass times velocity, the right-hand side of the equation represents the change in momentum. Most often, the mass of an object doesn't change, but its velocity can change. That would change its momentum. That change in momentum should equal the force that's applied to the object multiplied by the number of seconds that that force is applied. We call that impulse. So the impulse on an object will equal its momentum change. How does that come into play with a cart collision like we saw at the beginning of this video? Let's think about what happens when the carts interact. Initially, they're moving towards one another with a certain amount of speed, and then they hit. Let's zoom in a little bit and think about what happens when those two carts collide. They come into contact, so it would make sense that each cart is exerting a force on the other cart. Let's consider those forces. First, we have a force from the left cart on the right cart. I've represented that as a rightward pointing arrow. At the same time, the right cart would be pushing on the left cart to the left. Again, I've represented that as an arrow. We have to consider another of Newton's laws to understand what's happening here. Newton's third law is the law that says forces always come in pairs, equal in size and opposite in direction. So we can say something further about the two forces that are acting on the two carts. They have to be equal. I'll show that as a hash mark. So keep in mind, this cart on the left may be difficult to see, but it has some added mass. It's actually twice as massive as the cart on the right. Even though it's more massive and has more inertia, the force that it exerts on the right-hand cart is the same amount of force that the right-hand cart exerts on the left. The other thing we need to consider, besides the forces being equal, is the time interval over which they interact. These carts hit together over a certain amount of time, and those equal forces are applied simultaneously. So if we go back to our impulse equation and we think about the consequences of that, the force of each cart on the other cart is equal. The time interval is equal. That means the momentum change will also be equal. Momentum is a vector, so direction matters. The momentum change that happens on the right-hand cart must be equal to the momentum change of the left-hand cart. But the change in momentum is in a different direction. You could say the cart on the right is receiving a positive momentum change because the momentum change is towards the right. The cart on the left would be experiencing a negative momentum change, but the momentum change itself is equal. So the amount of momentum gained by the right-hand cart has to equal the amount of momentum lost by the cart on the left. Keep in mind that that doesn't mean the velocity change will be equal. The left-hand cart has a bigger mass, so to have an equal momentum change, its velocity change will actually be smaller. The less massive cart has less inertia. It experiences the same amount of momentum change, but because its mass is smaller, the delta V will be bigger. It experiences a bigger change in velocity. Since the amount of momentum gained by the one cart is equal to the amount of momentum lost by the other cart, the total momentum remains unchanged. If we tally up the momentum before the interaction and after the interaction, the total momentum will be equal. Conservation of momentum in equation form is sometimes represented like this. We've got our two objects that each have their own momentum, their mass times their velocity. If we add those two momentum values up before the interaction and after the interaction, they should be equal. It's important to note that when using this equation, velocities can be positive or negative. Usually we talk about a rightward velocity being positive and a leftward velocity being negative. In solving problems, you're usually given the mass of the object, so we know m1 and m2, and that doesn't change before and after. A lot of times we'll be given the velocity of the two objects before the interaction as well, so we are able to calculate a number for everything on the left-hand side. In a lot of problems, you'll know the velocity of one of the objects after the interaction, and you'll be asked to solve for the velocity of the other object. We have enough information on the right to calculate one of the momentum values. Our unknown is often v2, the velocity of the second object after the interaction. By plugging in values and solving, we can solve for that velocity. Some sources will show the momentum conservation equation like this. You'll see an apostrophe after the ending velocity of both objects. That's pronounced prime. So you would have pronounced this m1 v1 prime and m2 v2 prime. I actually like to organize my information in a momentum problem in a table. So I've got object 1 and 2, and I can calculate their momentum if I have enough information before the interaction and after the interaction. Again, a lot of times you'll have enough information to calculate the momentum of both objects before the interaction, and then you can total them up. A lot of times after the interaction, you'll know the velocity of one of the objects, but not the other. So you'll be able to calculate a number for the momentum in 3 of the 4 spaces in this table. You can just leave your unknown velocity as v. And then the important thing to note is that your total here, the total momentum of the objects before the interaction, must equal the total momentum of the objects after the interaction. You may also see problems where one of the objects is at rest before the interaction. That would just mean one of these boxes would be 0. It doesn't matter the mass of the object. If it's not moving, its momentum is 0. You may also see problems where the two objects stick together and move together after the interaction. If that's the case, v1 and v2 would have to be equal. Because the objects are stuck together, they're moving along at the same velocity. That should help you get started in solving momentum problems. Be sure to comment if you have any questions about the video. I'd also appreciate if you would subscribe to my channel so that you can get notifications when I post new videos. You'll see a link in just a moment. Thanks for watching.